Hello everyone, this is Sir Aris. Today, let us talk about um, applications of diagonalization. We consider a central conic section with center at the origin. So this could be an ellipse or hyperbola. This is the general form. A, B, H, and K are constants. So we can also write this in matrix form. Um, with this general equation, we can write x, y row matrix times the matrix with elements A, H, B, a square matrix, which is symmetric, and um, column matrix x, y. So if you want to verify, you can verify that this product of these three matrices would give us this, and this would be equal to K. So if we set this as M, then we have x, y times M times xy column equals K. We can also write the equation for the conic section, this one, in simpler form by choosing the principal axis as our reference axis. So what it means that is that if we have a say a coordinate system x, y, where your, for example, the hyperbola would look something like this. So the equation for this is a little bit complicated, but if we rotate our xy coordinate system so that the principal axis would be this, then we'll have a simpler form for our equation. So by simply rotating this by an angle theta, we can write our equation in simpler form. Um, we rotate the original axis xy to get by theta to get x prime, and this x prime y prime coincides with the principal axis of our conic section. So if you have, remember that if you have xy in terms or this is equal to um, some matrix multiplied to x prime y prime. And this would be our rotation matrix cosine theta, negative sine theta, sine theta, cosine theta. If we call this C, then we have xy equals C x prime y prime. Next step, we take the transpose. So taking the transpose of this equation, you have xy, take the transpose, you have xy equals these two matrices. They can take the transpose, you switch the positions, so this becomes from column, it becomes a row, and this becomes transpose. Okay, now since CT is equal to C inverse because C is orthogonal, then we have xy equals x prime y prime times C inverse. So we go back to using this, so xy m equals times xy equals k. So we replace this xy by this. We have x prime, y prime, c inverse times m. This xy we replace by this. You have c x y x prime y prime equals k. So we have this this equation. If C is the matrix which diagonalizes M, so if this C inverse MC is a diagonal matrix, then this equation is of the conic relative to this is the equation of the conic relative to its principal axis. So if you have the hyperbola here, um, applying diagonalization, we can uh, convert the equation for this hyperbola into one where the principal axis are this rotated axis. For example, transform the conic into a simpler form where the principal axis coincides with or principal axis coincide with the reference axis. Um, in matrix form, we have x, y, row matrix times 5 minus 2 minus 2, 2 times xy equals 30. The, the eigenvalue, so if this is our m, the eigenvalues of m are, this is something we have derived before, if I'm right. The eigenvalues are 1 and 6. So if C is a matrix that diagonalizes M, let's call that D. D is 1, 0, 0, 6. Okay. Now, if we have our X, our new um, coordinate system 1, 0, 0, 6, X prime, Y prime equals 30, then we have x prime squared. So if you do this operation, this becomes x prime squared plus 6 y prime squared equals 30. Um, you can also show that the this is just a side or bottom note that the rotation, this is something you can show, angle is um, arc cosine of 1 over square root of 5. You may want to verify that these two ellipses are, or if this is an equation for an ellipse, we can also um, check that this is also an equation of an ellipse by uh, plotting this. So the easiest way is to plot this in any web application. So for example, let me share a different screen. So if you type in Google online plot, okay, just choose whichever is convenient for you. For example, this graphing calculator. If we plot our original equation, that's 5x squared minus 4xy plus 2y squared equals 30. That is the ellipse for this equation. Now we rotate the axis so that the new form would look like um, x squared plus 6y squared equals 30. That would be another ellipse, but if this the axis for this ellipse is such that it coincides with the principal axis. So if this red ellipse here is being rotated, or the axis for this red ellipse is rotated, the new um, orientation of the ellipse would be this blue one. So the effect of diagonalization is to convert this difficult looking equation into simpler one, but um, so the simpler one, but with its axis being rotated. Okay, so let's go back to our discussion. Another example, find the characteristic vibration frequencies for the system of masses and the springs shown in this figure. So suppose this is a wall. Okay, and in that wall there's a spring attached with spring constant m, and on the right side of that m there's a mass, an object with mass, or the spring k is an object with mass m attached to a different spring but with the same spring constant k, and another object with the same mass m attached to another spring of the same spring constant k, and this is attached to um, another wall. This is fixed. This left side here is fixed. This right side is fixed. We want to find the characteristic vibration for the system of masses and springs shown. So first step, we let x and y be the coordinates of the two masses. So for example, if this is a position 0, then as it moves to the right, the position would be x. Okay, moves to the left, that would be negative x. So generally, so the movement of m would be uh, described. So the position of m, the displacement, would be described by this x. Okay, the magnitude of the displacement would always be this, the absolute value of x. On the other hand, here, let's say if this is at position 0, then as it moves to the right, the new position would be y. So it gets displaced by y. This one gets displaced by x. We can write the potential energy. If you recall potential energy of a spring, the potential energy of K is dependent on the movement of M. So if M moves to the right, then K is being stretched. If it moves to the left, it is being compressed by a value X. So for the leftmost spring, the potential energy is 1/2 spring constant K X squared. For the middle spring, the um, the potential energy is 1/2 K, the spring constant is K, but its compression or expansion depends on the position of the two masses. So let's say absolute value of x minus y would be its overall compression or expansion, and take the square, that would be the potential energy of the middle spring. And for the right spring, it would be v equals 1/2 k y squared. So the total potential energy is given by v equals 1/2 kx squared plus 1/2 kx minus y squared plus 1/2 ky squared. The force exerted on a mass is so attached to the spring is given by um, partial or negative partial derivative of v with respect to the compression, let's say x. So that would be the force. And so let me just write it neatly. Minus partial v with respect to x. Take note of the negative. So using um, the notation that x dot equals dx by dt, and x double dot is the second derivative of x with respect to time. So when there's single dot, first derivative with respect to time, double dot, second derivative with respect to time. So we can write m x double dot. X double dot is second derivative of x with respect to time. That's the acceleration. So ma, that's the force. So minus partial v with respect to x. That is for the mass on the left side. Okay. And taking the partial derivative of v with respect to x, we just solve for take the partial derivative of this. So that would be uh, kx okay, kx. Here there would also be another kx, so that becomes 2kx. There would be negative 1 half kxy times 2, so you would be left with ky, and the derivative of this is 0. So overall you'll have there will be a negative sign, so negative 2x plus there's a k plus ky, positive because of this minus sign here. Now on the y or for the second mass here on the right side, the displacement is y, double that, this acceleration, negative partial v with respect to y. And do the same process, there would be a negative x here, negative xy times 2, so 2 cancels, and you also have this plus the ky squared here. That would give you kx minus 2ky. So for this 2, we assume solutions x equals x naught ei omega t and y equals y naught ei omega t with the same frequency omega for both x and y. So this omega here is the angular frequency. So x dot would be, for this case, x times I omega ei omega t. X double dot would be x naught I omega squared ei omega t. I squared is negative this negative 1, so that's x naught omega squared ei omega t, and x double dot therefore is, so this x naught times this, that goes back to x, so this is negative omega squared x, and similarly y double dot is negative omega squared y. So we substitute this x double dot y double dot to here. You have m x double dot is negative omega squared x, that's negative 2kx minus or plus ky, and negative m omega squared y, that's kx minus 2 ky. Let's simplify this. We divide both sides for both equations by k. You have negative m omega squared kx equals negative 2 x plus y. Same thing for the second equation, m omega squared over k y equals kx minus 2ky. And this further, so if we set, okay, using lambda equals m omega squared over k, you have um, lambda xy, okay, so this two here is equal to 2 minus 1 minus 1 to xy. Okay, we multiply both sides by negative, um, so this becomes plus plus here. This is plus, this becomes minus, this becomes plus, this is minus. Okay, but there will be no more k here. K cancels, so minus x plus 2y. Here you have 2 minus 1 minus 1 2. So this would be your new equation. Okay, to find the eigenvalue, we write um, this to um, minus 1 minus 1 2 in matrix form, but in a different matrix, and take the determinant. So that different matrix would be a matrix where the elements in the diagonal is subtracted by lambda. Okay, lambda is um, the eigenvalue. So that eigenvalue is lambda also here. So this would be minus 1, 2 minus lambda. Take the determinant, set that to 0. Okay, so this would be 2 minus lambda, 2 minus lambda, so that's 4 minus 4 lambda plus lambda squared minus 1 equals 0. So that's 3 minus 4 lambda plus lambda squared equals 0. So this would be lambda minus 1 times lambda minus 3, which means that lambda equals 1 and 3. These are the eigenvalues. So the characteristic frequencies, or recall that since lambda equals m omega squared over k, then it means that omega equals um, lambda k over m, take the square root. Then the characteristic frequencies are, there are two eigenvalues, 1 and 3. So you have omega 1 is k over m if you use lambda equals 1, and omega 2 when lambda is 3, you have 3k over m, take the square root. We also need the eigenvectors. So the eigenvectors are, for lambda equals 1, say we set this to 1, that would give us x equals 2x minus y. y we can transfer to the other side, x transfer here, so that's x equals y. Okay, x equals y, so all points along the line x equals y, or if you want uh, to use a vector with unit length, it would be a vector r, um, not with unit length, but a simple vector would be, so one example would be that where the x and y components are both 1. Okay, for lambda equals 3, we set lambda to 3, so it's 3x, um, 2x, if we move that to the other side, we have x equals negative y. So all points um, along the line x uh, equals negative y, or for example, when r is 1 and has components 1 and minus 1. Okay, so for omega 1, that's what would, for an eigenvector, for example, this, or eigenvector x equals of eigenvectors are points along x equals y, such as this one. The two masses move together. Move together means moving together in the same direction. So if this is m at the first mass, this second mass, if one moves to the right, the other one also moves to the right. Okay, so they are attached by a spring. If one moves to the left, the other moves to the left. Okay, so this is one mode of vibration um, with an eigenvalue 1. Um, the mode of frequency is omega 1. The frequency is given by this. If that's the frequency, then the vibration would look like this. If one moves to the right, the other one moves to the right also. So they move together. One moves to the left, the other one moves to the left. For the second eigenvalue, omega 2, let's say the masses attached by spring, okay, same set of masses. If one moves inward, the other one moves inward also. Okay, so now one moves outward, so suppose same masses, but whose direction of motion would be one, the left side moves towards the wall, then the other side would also move towards the closer wall. So again, the first mode would be they move together. One moves to the right, the other one moves to the right. One moves to the left, the other one moves to the left. For the other mode of vibration, omega 2, the frequency is 3k over m square root. When one moves to the left, the other moves to the right. When the first one moves to the right, the other one moves to the left.